next doubt you have, next concept you have an issue with?
1 second.
So your elder brother is visiting now then.
Yeah.
Visiting or he stays here with you?
No, he's visiting.
Visiting, okay. Where is he working?
He's not working anywhere yet.
Okay.
Soon.
Hmm.
Sir, can you explain electromagnetic effect once?
What did you understand by it so far?
Well, like we were told that in the presence of a reagent, then it
So your
like
doubts basically stem from the fact that what does the entire statement really mean? Why that statement is that way?
yeah.
Okay, fair enough. So let's talk about a molecule. Okay, so
Yeah.
in a molecule, let's say we are going to be having different types of bonds. Okay, so when there are different types of bonds available, let's say that molecule is about to react. Then when a molecule is about to react, something has to happen during the reaction, correct?
Hmm.
What will usually happen during a reaction? Some bonds must break, some bonds must
Yes, exactly. Yeah.
break. So some bonds must break.
Yes, sir. Yeah.
So if some bonds must break, if I'm going to ask you to react and form a product, I want you to make a change in yourself and be a changed person tomorrow. What will you do?
Change the least affecting thing.
What is that?
Uh,
You'll break your leg?
yeah.
No.
Like,
You'll cut
no,
your
no,
hand.
no. Here, yeah. I was thinking here. Yeah.
You'll cut your nails. You'll paint your
Nails.
face. So the
Nails.
idea here is you will do the one which is going to be easiest for you to do,
Yes, sir.
or the easiest bond for you to break, you break that.
Okay, that's why.
So in a molecule where there is sigma bonds and pi bonds, pi
Hmm.
bonds are usually the weaker fellows every time.
Yeah.
So if the molecule is going to be reacting, it will usually react at the location where the pi bond is present, because that guy is the easiest to break.
Yeah. Yeah.
Okay. So far, you have understood that part now. Next thing, when it comes to pi bonds, what kind of a location is a center which is having a pi bond, a location which is having a pi bond? So if I have, say, a carbon-carbon pi bond in a molecule,
Hmm.
what type of a location is that in the molecule?
Outside the plane of the molecule. Like,
No. You're not
hmm.
understanding my question here. Imagine a building. Okay. My molecule itself is represented by a huge building. Okay. Now, in that building, what will the pi bonded location of the molecule look like or feel like?
Restrict. Like,
There will be restricted rotation,
yes, that's right. Yeah.
but there will be a lot of free electron density available.
Fear tendency. Yes.
Microde,
Yeah.
which is not that tightly held on over here.
Yeah.
Correct?
Yeah.
So, effectively speaking, it is a location which is more tight. Restrictions are there, but there is a large amount of electron density floating around in a relatively loose manner. Correct? So, effectively speaking, this is a location where there is a concentration of electron density in the molecule
Hmm.
compared to the other locations.
Yes, sir. Yeah.
So, what type of systems will be attracted to this place?
Electron deficient.
Good. So electron deficient fellows will be attracted to this guy here.
Yes, sir.
Now comes the next part of the question here. If I'm going to be having a pi center available, okay, what I'm going to be now having is I have now accepted, or rather, I have now hopefully convinced you into understanding that the pi bonded location in a molecule is the one which is going to be targeted first. Why? Because that is the one which is easiest to break. First one. Next, when a pi bonded center is to be considered, in normal cases, the pi bonded center is a center of extra rich electron density. Normal conditions, like a C double bond C or a C triple bond C. So, what kind of a system is it going to be more strongly attracted towards? It will be attracted towards electron deficient systems. But that is not the case for all pi bonds. There are some pi bonds which will be attracted towards electron rich species also. We'll talk about that in a bit. But when I have any pi clouded center, what happens in that particular case there is that particular pi cloud center is going to be something which is going to be susceptible to attack predominantly. When an attack happens on it, the pi cloud is something which is very easy to shift around. It is not that tightly bound. So it simply moves in the direction which suits the electron shift which is going to be happening. Let me make that point a little bit more clearer. So if I have, say, a C double bond C type of system available, okay, this is a center where there is going to be a pi cloud available, where originally it is like this. So effectively, you have a sigma bond over here, and you'll have a pi cloud which is going to be floating above and below. Diagram is poor. So I'm just going to scrap the diagram completely. We'll go with the basics itself. So if I'm having a C double bond C available, then I'm going to be having an electrophile attacking it. An electrophile is something which is electron poor and is interested in extra electron density. So in that particular case, the pi cloud will shift towards the attacking electrophile so that that attack can happen more easily. Or you can think of it as, because the electrophile is coming, that particular pi cloud is shifting. You can think either way. You can think of it as electrophile is coming and hence the pi cloud is shifting to go meet it. Or you can think of it as, because the electrophile is going to be moving in that direction, the pi cloud is also moving in to facilitate that attack to happen in a better manner. Both ways are perfectly fine. Okay, so the idea is, you effectively have to simply apply physics over here. The pi cloud has to be attacked. So it will do what it can to favor the attack. Why should it be attacked? Because that is the easiest place to target. No other reason.
Okay. Yeah.
In this particular case here, if a nucleophile targets it. Now, a nucleophile will never target something like this, but it will target it like this. If a carbon and an oxygen are present, this carbon will have a high delta plus.
Yeah, it wants to get positive.
So when a nucleophile is targeting this, now what will happen? The pi cloud will shift away from the attacking fellow. So this shift, where it is shifting towards the attacker, shift towards attacker, this is called plus electromeric effect. And in this case, shift away from attacker.
See.
This is minus E effect. As simple as that. Nothing more, nothing less.
Okay.
You're clear with this?
Yes, sir. Clear.
Now, next. Next to
uh, that's about it.
that's about it.
Yeah.
Seriously,
Yeah.
give me a second.
Yeah. Oh, sir.
Yes.
Yeah. Sir, in resonance, we were told that linear resonance will be given more priority than it will be stronger than cross resonance. Like,
Okay. Hmm.
why is that so? Like,
Give me the example you saw.
uh, sir, 135 hexi triene. Yeah. Hexa 13. Yeah. Is it?
I'm guessing you saw something like this.
Yeah, something like that.
Hmm?
Yeah.
Were these the rough cases you saw?
Yes, sir. Yeah.
So, what do you understand by resonance?
Uh, like,
How should you visualize it image wise? So,
uh,
you've discussed what is aromaticity already?
yes, sir. Huh.
Aromaticity is done for you so far.
Yeah, to an extent. Yeah.
So, your teacher has already discussed what is aromaticity.
Huh.
Okay, so explain what is aromaticity, what is resonance.
Uh, sir, we didn't go much into depth about aromaticity. Like, I'm not sure too
Okay,
much
all
about
right,
that.
okay, all right. Let's go into resonance itself.
Hmm.
So, when it comes to resonance here, in this particular question which you have asked, there are many ways of looking at the answer for this. A very simple way of looking at the answer would be to just draw the resonating structures.
Hmm.
All right. So, when you're drawing the resonating structures, you will literally get more stable resonating structures for this compared to this. Why? Because in this here, you will end up having this location being the pain center more often. Do you understand what I mean by pain center? There has to be resonance now. It has to be this way or it has to be this way, correct?
Yeah.
So either this end and this end will be pain center, or it will be this particular ending and this particular ending which will be pain center. Correct? When I say
Yeah.
pain center, I mean something which has a charge.
Yeah. Hmm.
So the
Yes,
same
correct.
location technically ends up getting a charge every time. Right?
Yes, sir.
In this here, it will be shared by all of them nicely. Right?
Hmm. Yes.
So the pain center gets distributed equally well in all of these cases. That is basically the idea here. So in the linear thing there, the pain basically or the charges, When I say pane here, I mean the locations which are charged in the resonating structures. When you draw resonating structures, different carbons will take the charges, correct? Among the charges, which charge is more stable? Minus is more stable than a plus. Because in a minus there is octet, in a plus there is no octet.
Yeah.
Correct. So when you're drawing the resonating structures, there are pane centers created every time you draw a resonating structure. Pane centers are those which are going to be having charges. So among those pane centers, if the same location is having the pane more number of times in the resonating structures, that is less stable. You understand the idea here?
Yes.
Or not?
Yeah.
You want another metaphor, or you're clear with what we've talked about already?
I understood.
Okay. Now, let's look at another way of understanding resonance. I asked you about a visualization with respect to resonance, correct?
Yes, sir.
The best way to imagine or visualize resonance is like a flow of water, which is rushing from different tanks. Yes, sorry?
Nothing.
You were visualizing something just now?
No, nothing.
You're pointing something to your brother?
No.
Then what did he mean by this? I'm curious because that symbol is something which did.
Flowing, I'm saying. Like water in different paths.
That's basically the exact thing which I'm looking at over here. That's why I was interested in what you showed that time. Because the flow is what is important over here. So the idea here
different
is
pathways.
So effectively, you're going to be having different tanks present, and these tanks are connected by pipes. And water is flowing between these tanks. The more stagnant the water is going to be, the less stable the system is going to be. The more the water is going to be constantly flowing, the better the stability of the system is. In this case here, the water is of course going to be your analogy with respect to your electron flow here. So if I'm going to be having a molecule like this is going to be a long stream. So there is going to be lesser stoppage of the flow of electron density. It is like a clean, smooth flow. All right. So it's going to be a clean, smooth flow where the flow is only having two real problem areas. What are the two problem areas where the water or the flow will become stagnant? In this molecule, what are the two areas where the flow of electron density will become stagnant? The two corners.
Middle. Yeah. Oh, sorry.
The two corners predominantly. You will also have these two middles also being small spots, but they're not going to be that much.
Okay.
The two corners are going to be the real spots where the electron flow has to turn around. And it will obviously be something which is going to be slowed down over there. So however fast the turning is going to be for the flow there, it is still going to be turning. So if it is turning at a depression, it is going to be slowing down. The more it slows down there, the more stagnant that particular region is, the less stable it is. Density or the flow of electron density gets stagnated to some extent. When I say stagnated, it is slowing down. So you can either think of these locations where the carbons are present as either depressions in a field or as hills in a field. Either way, when the flow of electron is going through there, it will slow down as it is going down and then coming up, or as it is going up and going down. You understand what I mean by that now?
Yes.
I'm not sure whether I got through to you. Now, in this here, what's the problem here in this second structure here? In this second structure, the real problem is that there is a flow like this, and then there is a flow like this.
Interesting.
It is getting stuck over here predominantly.
Okay,
That
okay,
is going to be
understood.
a much larger pain center, which is needlessly created.
Oh, okay, okay,
That
okay.
is the reason why it is going to be a problem. That is what you are getting when you do resonating structure also.
Yes, sir.
When you
Yes.
draw the resonating structure, if the resonating structures are drawn following the rules properly, they will give you a clearer idea as to what your visualization tells you. Your
Yeah.
visualization is to help you build instinct towards it. What is instinct? Instinct is basically what you have visualized already. You plot the coordinates on that map and you think the next step is directly predictable. That is instinct. In this case here, you need to build the correct visualization so that your instinct with respect to these things are built up correctly. If you build the
Okay.
wrong visualization, your instincts will not be built correctly. They will point you in the wrong direction there. So you understand how this particular thing works out over here? Is this clear properly?
Yes, sir.
Okay, next one.
Mm,
Are there any topics to discuss at all? Because we have like another maybe 10-15 minutes max. So if there are any larger chunks, let me know. Otherwise, if you have only these kind of, small territories which we need to chart out more properly, we can continue with this itself.